start recording. So today we'll start the next unit, which is diffraction, and this is the last unit in which there are lengthy derivations, and after that we'll be done with the longer derivations. You might already be familiar with the term diffraction. It's basically bending of the light around the corners, or when you pass the light through any particular hole. And here the condition is that the size of that particular aperture has to be finite size, right? Agar wo point hole hoga, and in that case if you have such 2-point holes, that would lead to basically Young's double slit interference pattern here. Diffraction, your slit width has to be finite, or the aperture through which you are making light pass, that has to be basically finite. So in that way, we can define diffraction as basically either spreading out or bending of the light around the corners, or as they pass by some objects, or through a finite width aperture. That is basically going to be your diffraction. An example of that is, for example, if you take here and if you have the plane wavefronts coming from here onwards, you will see your wavefronts further going in this way. And I believe that you are already familiar with wavefronts, how the planar wavefronts are being generated. So it's basically like saying you have this kind of wave over here, and assume that the wavelength is same, just ignore my drawing here. And in that case, what you can say is that at all the points where your displacement is same, you can join all the points. And in that case, you will get the straight line here. And that would basically correspond to your planar wavefront. And then you say, aapka jo wavefront hai, it is of the form of a plane, and उस planar wavefront के साथ आपकी जो wave है वो forward direction में basically move कर रही है. So that is meant by planar wavefront. You can have circular wavefront also. अगर आपके पास में कोई point source है, and if you are sitting very close to the point source, then you will have kind of spherical wavefront or circular wavefronts also. Diffraction is basically, before we go into the details of the single slit diffraction, double slit, and then N slit diffraction pattern, before we go there, there is Huygens principle. Which basically states that on this wavefront, the wavefront that we have defined over here, every single point on this wavefront is going to act as a source of secondary wavelets. And those secondary wavelets, they are going to move only on the forward direction. So if every single point is going to act as a source of secondary wavelets, and let's say I had drawn some finite amount of point over here, and I can start secondary wavelets from all these points over here, and then this principle basically states that you can draw the tangent that would basically be these wavelets over here, and then this will be your next wavefront. Again, on this wavefront, every single point is going to act as a source of secondary disturbances. फिर से आपके secondary disturbances होंगे, उन secondary disturbances पे आप फिर से tangent draw कर दोगे, and that would be your next wavefront. So this was basically your Huygens principle, which basically states that on these wavefronts, every single point, if of course it is not obstructed by something, is going to act as a source of secondary wavelets, and these secondary wavelets are going to move only in the forward hemisphere. ये सिर्फ आपके forward hemisphere में move करेंगे, and that's basically how your wavefronts propagate in space. आपके wavefronts हैं space में इस way में propagate करेंगे. Diffraction is in a way similar to interference in the sense दोनों में आपका waves का superposition होता है. Interference में भी आपकी जो दो rays हैं वो superimpose करती हैं. Diffraction में भी 2 or more rays हैं वो superimpose करती हैं. But diffraction is different than interference in a certain number of waves. For example, interference में आपके जो maximum की intensity है वो आपकी constant रहेगी. It would be something like this. Whereas अगर आप diffraction में बात करो, you might be already familiar कि diffraction में आपके पास में एक central maxima होगा, and फिर उसके बाद में आपके पास में जो सेकेंडरी मैक्सिमा होंगे उनकी इंटेंसिटी जो है दैट वुड कीप ऑन डिकेइंग एज यू मूव अवे फ्रॉम द सेंट्रल मैक्सिमा. So your intensity distribution is going to be different in interference and the diffraction. In interference, usually your points of the minima, your intensity is zero at the points of minima, and that is usually not in the case of diffraction. In the case of diffraction, your minima are not perfectly dark. The third difference could be that the fringe width, we talked about the fringe width when we are talking about the wedge shaped film, they are more or less constant in interference, which basically means that अगर आप interference से इस minima और इस minima के बीच में distance calculate करोगे या इस minima और इस minima के बीच में distance calculate करोगे, that is going to remain the same. But that is not the case with diffraction. For example, diffraction में आपका जो central maxima होगा उसकी width अलग होगी, उसके बाद में आपका जो first मैक्सिमा होगा उसकी विड्थ आपकी अलग होगी, सेकंड की प्रोबेबली अलग होगी, थर्ड की अलग होगी, एंड सो ऑन. So these are some of the differences between interference and diffraction. Even though the kind of at the end of the day, these are the rays or the waves which are super electromagnetic waves which are basically superimposing on the top of each other. चाहे वो आपका interference हो, चाहे वो आपका diffraction हो. इंटरफेरेंस में क्या होगा, आपके दो डिफरेंट वेव फ्रंट से आपका जो है सुपरपोजिशन बेसिकली वेव्स का होता है. फॉर एग्जांपल, अगर आप पैरेलल थिन फिल्म की अगर आप बात करते हो, इन द केस ऑफ पैरेलल थिन फिल्म आपका एक वेव फ्रंट इस रे के लिए होगा, आपका सेकेंड वेव फ्रंट जो है वो सेकेंड वाली रे के लिए होगा. इन द केस ऑफ डायफ्रैक्शन, अगर आप डायफ्रैक्शन की बात करते हो तो आपके पास में सेम वेव फ्रंट होगा. अगर आप सिंगल स्लिट डायफ्रैक्शन की बात करते हो, सो यू हैव द सेम वेव फ्रंट. उस सेम वेव फ्रंट से आपके जो सेकेंडरी वेवलेट्स प्रोड्यूस होंगे उसके बीच में जो आपकी वेवलेट्स प्रोड्यूस होंगे उनके बीच में आपका सुपरपोजिशन होता है. सो you still have the coherent sources in both of the cases, but यहाँ पे आपके अलग-अलग wave fronts हैं. In the case of interference, in the case of diffraction, you are basically starting with the same single wave front, and that wave front, on that particular wave front, there are secondary wavelets as per Huygens principle, and those secondary wavelets basically kind of superimpose on each other, and that give you some kind of resultant intensity distribution on the screen, and that leads to your diffraction pattern over here. In simple terms, you can say that basically, if, for example, if you talk about two slits and I have a screen here, what do we expect on the screen? Do I expect a diffraction pattern? Do I expect an interference? Or do I expect a superposition of both of them on this screen? That would basically depend on the size of these slits. If these slits are point slits, in that case, you will get the result of your Young's double slit interference pattern. On the other hand, if these slits have finite width, in that case, on the screen, what would you see? That would be a kind of superposition of diffraction and interference. अगर आपकी स्लिट साइज फाइनाइट है तो आपको स्क्रीन पे जो पैटर्न दिखाई देगा वो सुपरपोजिशन होगा डायफ्रैक्शन और इंटरफेरेंस का. इस स्लिट में डायफ्रैक्शन होगा, इस स्लिट में डायफ्रैक्शन होगा, इस स्लिट और इस स्लिट के बीच में इंटरफेरेंस पैटर्न भी होगा. उन दोनों को आप will do the mathematics behind it, and the resultant over here would be basically a kind of intensity distribution which is decided by both interference as well as diffraction. So it's all about the slit size. What is the size of slit that you are choosing? That would decide that if you will be seeing on the screen an interference pattern or the diffraction pattern. As I said before, in the case of diffraction, we say that our slit size is going to be a finite slit size. So for the rest of this diffraction unit, I'm going to believe that you know that the slit size is going to be a finite slit size here. In the diffraction, then there are further two types of diffraction. The first kind of diffraction is called as Fresnel diffraction. In this diffraction, you basically say that either source of light or screen or both of them are at a finite distance from the slit. Which basically means that I'm saying if this is your slit, then your source is at a finite distance, or your screen is at finite distance, or both of them are at finite distance with respect to the slit here. So this diffraction pattern that you will be seeing on this screen is going to be Fresnel diffraction pattern. Any of them or both of them are at finite distance from the slit. The second kind of diffraction pattern is Fraunhofer kind of diffraction pattern that we are going to discuss here. And here the condition is that both your slit, your source as well as screen has to be at infinite distance. So what you do basically is that if this is your slit, you have the source somewhere here, you can place a convex lens here. Your light ray here would look as if they are coming from a source which is placed at an infinite distance. Somewhere here would be your screen. You again place a convex lens here so that it would again seem as if your screen is at an infinite distance from the slit also. So this would be your source, this is going to be a slit, and this is going to be a screen. In Fraunhofer diffraction pattern, both this source as well as this screen has to be at an infinite distance from the slit. आपका source, screen दोनों को slit से infinite distance पे होना चाहिए. We are going to talk about single slit, double slit, and N-slit diffraction pattern. N-slit is basically your diffraction grating, and that is your DVD. आप DVD को अगर लाइट में देखते हैं जो बहुत सारे आपको कलर्स दिखते हैं, that is basically due to N-slit diffraction pattern. We'll start with the single slit.
Ma'am,
हाँ जी.
Ma'am, can you show the previous slide?
Yeah, sure.
Thank you, ma'am.
So we'll start with the single slit. I'll do the proper mathematics for the single slit. After that, when we move to the double slit and then we move to N slit, I'm going to say that, okay, this was the derivation we derived for the single slit. अगर आप दो slit लोगे तो आपकी दोनों एक single slit का लूंगी मैं दूसरा single slit का लूंगी और दोनों का amplitude में simply add कर दूंगी. And similarly, जब हम N slit का करेंगे, I'll say that, okay, we have already derived the expression for the single slit. Now what I have to do is that I have to add the expression for the single slit n number of times. Of course, with proper phase factor, I'll take into account before doing that. But the mathematics part, the core mathematics, will do only for the single slit. And then when we'll go to the double slit, there would be not much mathematics involved over there. So therefore, I suggest that you pay attention to the single slit here. Single slit, I'm going to say that it is kind of an infinitely long slit, which basically means that if I have a slit here, and this is going to be the width of the slit here. B is the width of the slit. And this is going to be the length of the slit. Which basically means that the length of the slit is going to be much larger as compared to the width of the slit. अब जब मैं इसको screen पे plot करूंगी या when I'm going to draw it on the screen, what I'm going to do is I'm going to draw it in this way, and I'm going to say that this is the width of the slit, which is basically this is B here. So imagine these two lines, this line and this line, coming out of your screen and going up to infinite distance or up to a very large distances. So B is going to be the width of the slit here. Now, since I'm going to talk about the single slit now, and I should do it on the probably next page. I need more space to draw this diagram. Let's talk about the single slit. So I'm saying that there are parallel rays which are incident on this single slit, right? I don't care where is the source. The source, of course, has to be at an infinite distance. And agar, because really it is not possible to place source at infinite distance. That means source is somewhere at a finite distance, and source or slit ke beech mein you have somewhere placed a convex lens here. And let's say this is your screen here, where you will be seeing the intensity distribution basically. So what I'm going to do is that this slit from here to here, and this is, let's say, point A1, and this is point AN. So we know that the width of this slit I have said is equal to B from the previous slide. So this is the width of the slit, and when I'm drawing it in kind of more 2D, then this is how I'm representing the width of the slit. Again, imagine it coming out of your screen and going to the very large distances over here. That would be the length of the slit here. Here somewhere you have placed a plano-convex lens, because after diffraction, your lights is going to bend and they will be bending parallelly. So you need to converge them to some point on the screen here. Let's say that you want to look at this point P. So A1 से क्या होगा, आपकी light bend होगी lens में जाके, and then let's say it did come to P over here. And then what I can do is that for simplicity here, for just our own convenience, I am going to divide this slit into n number of points. Of course, it's a finite width slit, and किसी भी width को अगर आप points में divide कर रहे हो, you have to take infinite number of points. But right now, I'm going to divide it into finite number of points, and then in the end, I'll say that let us let n run to infinity. Let me repeat that. Right now, I'm saying that I'm going to divide it into n number of points. Once we have done our derivation or mathematics, then I'll say that your n basically tends to infinity. And then we will conclude our results from that point onward. Just to simplify the mathematics, now we are dividing it into certain number of points over here. Let's say this light basically here bends by an angle theta. If this is bending by theta, the wavelets that will be originating from A2, they will also bend by the same theta. A3 से भी जो आपके bend होंगे, वो भी आपके theta से ही bend होंगे. All the wavelets, they are going to bend by the same angle theta here. And point P पे क्या होगा, आपको जो भी amplitude दिखाई देगा. And now when I'm saying amplitude, that means amplitude of electric field या magnetic field. वो जो resultant आपको amplitude दिखाई देगा, वो जो secondary wavelets इन सब points से start हुए हैं, उनका superposition होगा. Basically, on the screen at point P, whatever amplitudes will be whatever displacements you will be seeing at point P, that would be basically a superposition of wavelets which are starting from A1, A2, A3, A4 up to AN. वो सारे के सारे आपको superpose करके कुछ resultant आपको amplitude या displacement दे देंगे, and आपका जो intensity है that is directly proportional to amplitude square, and that you actually do not see amplitude or displacement on P, you see the intensity, and intensity is directly proportional to amplitude square. So eventually we are interested in getting the expression for the intensity at this point P. Now from A1 to A2, right? It is obvious that the wavelets that are going to start from A2, they are going to travel certain amount of extra distances as compared to A1. A1 से जो आपके वेवलेट स्टार्ट होंगे वो मिनिमम डिस्टेंस ट्रेवल करेंगे. A2 से जो स्टार्ट होंगे वो A1 से स्लाइटली ज्यादा डिस्टेंस ट्रेवल करेंगे. A3 से होंगे वो A1 और A2 के कंपैरिजन में ज्यादा डिस्टेंस ट्रेवल करेंगे. AN से जो आपके वेवलेट स्टार्ट होंगे वो मैक्सिमम डिस्टेंस ट्रेवल करेंगे बेसिकली. So what I can do in that case is you can draw a perpendicular from here to here. अगर आप यहाँ से यहाँ पे एक perpendicular draw कर देते हैं. Now from this point onwards, let's call this point as A2 prime. After A2 prime, इस line के बाद में these two lines, they are basically parallel to each other. So they are going to travel equal amount of distances. That means whatever extra distance A2, the wavelets that were starting from A2 are traveling, that extra distance is A2, A2 prime. That is the extra distance which is being traveled by wavelets starting from A2 as compared to A1. A1 से जो आपके वेवलेट स्टार्ट होंगे उनके साथ में A2 से जो वेवलेट स्टार्ट होंगे उनके कंपैरिजन में they are going to travel this much extra distance over here. Now let's say that these points, they are equally spaced with respect to each other. So let's say that the separation between these 2 points is delta. A2 और A3 के बीच में भी सेपरेशन डेल्टा है, A3 और A4 के बीच में भी सेपरेशन डेल्टा है. That means अगर मैं A1 और A3 के बीच में separation calculate करूं, A1 to A3, your separation would be delta plus delta 2 times delta. So A1 A2 is basically delta. A1 A3 is going to be 2 times delta. A1 A4 is going to be 3 delta. How about A1 AN? यहाँ पे 2 था तो यहाँ पे 1 था, 3 था तो 2 था, 4 था तो 3 था. When it is n, it is going to be n minus 1 times delta. Right? That would be your separation from here to here. And of course, if you say that n tends to infinity, in the limit when your n tends to infinity, the separation between these 2 points would tend to 0. If your n tends to infinity, in that case, your delta would tend to 0. क्योंकि जैसे जैसे आप नंबर ऑफ पॉइंट्स बढ़ाते चले जाओगे, पॉइंट्स के बीच में सेपरेशन जो है वो कम होती चली जाएगी. और इफ यू आर सेइंग द नंबर ऑफ पॉइंट्स आर इनफाइनाइट, तो उनके बीच में सेपरेशन है वो आपकी उस केस में 0 हो जाएगी. So here we said A2 prime is the extra distance traveled over here. Now let me draw this triangle again. This angle is theta here, and this is the perpendicular here. This is also perpendicular, right? This from here to here. If I can draw a bit clear it somewhere here. So I'm saying that this is your A1, this is your A2. यहाँ से मैंने इसके ऊपर एक perpendicular draw किया है. And then I'm saying if this angle is theta, that means by default this angle is going to be 90 minus theta. क्योंकि ये जो है ये perpendicular है. ये 90 minus theta है. So this is going to be theta. Which basically means that I'm saying that this angle is going to be theta. This angle is going to be theta. Right? Now from here, I want to know what is this A2 prime, the extra distance which is traveled by the wavelet starting from A2. So A2 prime upon A1 A2. This is perpendicular and this is going to be your hypotenuse. This is basically equal to sine of theta, which means that A2 prime is equal to A1 A2. A1 A2 is nothing but delta is equal to delta sine theta. ये आपका delta sine theta के equal हो गया. Now, similarly, you can draw a perpendicular from A1 to A3. अगर आप A1 से A3 पे एक perpendicular draw करते हैं, and let's say it intersects this wavelets starting from A3 at A3 prime. ये एंगल तो अभी भी आपका थीटा है, right? I can still say that A3 prime upon A1 A3 is equal to sine theta. Now I am talking about basically this triangle. This would mean that your A3 prime is equal to A1 A3, which is distance from here to here, delta plus delta, 2 times delta sine theta. From here, जब आपका A2 पे आप आए तो 1 डेल्टा साइन थीटा था, A3 पे आए तो 2 डेल्टा साइन थीटा हो गया। दिस मीन्स दैट अगर अब मैं यहां से यहां पे अगर मैं परपेंडिकुलर ड्रॉ कर दूं, विच इज द लास्ट पॉइंट हियर, सो यहां से यहां के बीच में जो आपका डिस्टेंस है A1 टू AN, दैट इज बेसिकली इक्वल टू n-1 डेल्टा। सो ये वाला जो डिस्टेंस है वो आपका n-1 डेल्टा है। और अगर मैं इस पॉइंट को an प्राइम कह दूं, देन आई कैन से दैट an प्राइम अपॉन a1 an is also equal to sin theta, which would mean that an prime is basically equal to n-1 delta sin theta. So you see a pattern here. यहां से A2 से जो वेवलेट होंगी वो डेल्टा साइन थीटा एक्स्ट्रा ट्रेवल करेंगी। A3 से जो आपकी वेवलेट स्टार्ट होंगी वो आपकी 2 टाइम डेल्टा साइन थीटा एक्स्ट्रा डिस्टेंस ट्रेवल करेंगी। सिमिलरली जो आपकी A4 से होंगी वो फिर आपकी 3 टाइम डेल्टा साइन थीटा एक्स्ट्रा डिस्टेंस ट्रेवल करेंगी एंड सो ऑन। और जो लास्ट वाला पॉइंट से जो वेवलेट स्टार्ट होंगी वो आपकी इतना डिस्टेंस एक्स्ट्रा ट्रेवल करेंगी, राइट? क्योंकि यहां से तो आपने परपेंडिकुलर ड्रॉ कर दिया, इसके बाद में दोनों रे पैरेलल है और दोनों इक्वल डिस्टेंसेस ट्रेवल करेंगी। So all we have to do is take into account the extra distances traveled by the wavelets which are originating from the different points here. Now, what you can do is that we did that in interference also. You can convert the path length into the phase and phase into path length, right? Let me repeat that. We can convert phase into path length and path length into phase. So what I am basically saying is that we say that here the wavelets which are starting from A to A2 prime, they are traveling the distances which are basically equal to, let me write it here itself. So what we are saying that the wavelets which are starting from here, they are traveling this much extra distance. You know that 2 pi is equivalent to lambda, right? If your lambda corresponds to 2 pi in phase, या तो आप इतना पाथ लेंथ लैम्डा ऐड कर दो या आप फेज में इतना एंगल ऐड कर दो, तो बेसिकली आपको सेम मिल जाएगा। सो लैम्डा अगर आप पाथ लेंथ के लिए 2 पाई अगर फेज आपको एक्स्ट्रा इंट्रोड्यूस करना पड़ेगा तो 1 के लिए आपको 2 पाई बाई लैम्डा करना पड़ेगा। डेल्टा साइन थीटा के लिए आपको जो फेज एक्स्ट्रा इंट्रोड्यूस करना पड़ेगा दैट वुड बी 2 पाई बाई लैम्डा इनटू डेल्टा साइन थीटा। इतना एक्स्ट्रा फेज जो है वो आपको इंट्रोड्यूस कराना पड़ेगा। हाउ विल इंट्रोड्यूस दिस एक्स्ट्रा फेज? आई विल टेल यू। सो फॉर A1 से जो आपके वेवलेट स्टार्ट होंगे, लेट्स से दे आर गोइंग टू बी ऑफ दिस फॉर्म, वो आपके इस फॉर्म में होंगे, राइट? इलेक्ट्रोमैग्नेटिक वेव से हमको पता है कि आपका इलेक्ट्रिक फील्ड मैग्नेटिक फील्ड साइनोसाइडल फॉर्म में होता है, एंड दिस इज व्हाट आई एम यूजिंग हियर, कि आपके A1 से जो भी इलेक्ट्रिक फील्ड की वजह से जो डिस्प्लेसमेंट्स होंगे because of the wavelets which are originating from point A1, they will be of this form. A2 से आपकी जो wavelets होंगी, so either I can add some extra path length into the wavelets that are starting from A2, or what I can do is that I can introduce this phase here, where this phase is nothing but equivalent to 2 pi by lambda into delta sine theta. So we are basically saying कि जो wavelets आपके point A2 से start होंगी वो A1 से जो wavelets start होंगी उसके with respect to इतना phase में lag करेगा। phase में lag तभी करेगा तब वो extra distance travel कर रहा होगा, that is why the minus sign here. इसलिए हमने यहाँ पे माइनस साइन लगाया है, क्योंकि A2 से जो वेवलेट्स यहाँ पे स्टार्ट होंगी वो एक्स्ट्रा डिस्टेंस ट्रेवल करेंगी, दे आर गोइंग टू लैग बिहाइंड एज कंपेयर टू द वेवलेट्स व्हिच आर स्टार्टिंग फ्रॉम पॉइंट A1। सिमिलरली अगर आप अब A3 की बात करते हो, अगर मैंने डेल्टा यहाँ पे डेल्टा साइन थीटा की वजह से हमारा जो फेज हमने इंट्रोड्यूस किया, अगर मैंने इसको फाई कह दिया है, तो यहाँ पे नेक्स्ट वाला जो आपका है 2 डेल्टा साइन थीटा है, तो उसकी अगर इसकी वजह से जो आपका फेज आया है वो अगर आपका फाई आया है, तो इसकी वजह से जो फेज आएगा वो आपका 2 फाई आ जाएगा। 3 टाइम्स डेल्टा साइन थीटा की वजह से जो आपका फेज आएगा वो 3 टाइम्स फाई आ जाएगा। n-1 डेल्टा साइन थीटा की वजह से जो आपका फेज एक्स्ट्रा इंट्रोड्यूस होगा वो आपका n-1 फाई हो जाएगा। किसी को यहाँ पे पता ना चला हो मैंने क्या किया है? It's even though it's simple mathematics, but it's a bit tricky mathematics. So then I'm saying A3 से जो मेरी wavelet start होंगी, they will be of this form. A4 से जो होंगी, they will be of this form. And so on. And finally AN point से जो होंगी, वो होंगी cos of omega t minus 2 से हुआ तो 1 5 सब्ट्रैक्ट किया, 3 से हुआ तो 2 5 हुआ, 4 से हुआ तो 3 5 हुआ, n से होगा तो n-1 5 होगा। और पॉइंट P आपका जो स्क्रीन पे है, यहाँ पे आप जो डिस्प्लेसमेंट ऑब्जर्व करोगे वो तो इन सब पॉइंट्स की वजह से बेसिकली सुपरपोजिशन होगा आपका। सो पॉइंट P पे जो आप ऑब्जर्व करोगे डिस्प्लेसमेंट एट पॉइंट P, वो आपका इन सब का सम होगा बेसिकली। A1 की वजह से जो डिस्टर्बेंसेस आएंगे प्लस A2 की वजह से जो डिस्टर्बेंसेस आएंगे, A3 की वजह से जो डिस्टर्बेंसेस आएंगे, प्लस जो लास्ट वाला पॉइंट है उसकी वजह से जो डिस्टर्बेंसेस आएंगे। सो व्हाट यू विल हैव इज समथिंग लाइक दिस, सिंपली इनका सम होगा। So on A of cosine of omega t minus n-1 phi, ये आपका रिजल्टेंट डिस्प्लेसमेंट आएगा पॉइंट P पे। डिस्प्लेसमेंट ऑफ व्हाट? डिस्प्लेसमेंट ऑफ इलेक्ट्रिक फील्ड या मैग्नेटिक फील्ड, किसी का भी आप डिस्प्लेसमेंट की ये बात कर सकते हो। Notice down this value of phi. I'm going to use it again and again in double slit and slit everywhere. We'll use it time and again to get the condition of minima and maxima. Now this summation series, it's a trigonometric summation series. इसका अगर आप solution बात करते हो, and let's call this as E. This resultant displacement is going to be equal to A. ये जो trigonometric series है, इसका sum is given by sine. यहाँ पे number of terms आप count करो, 1, 2, 3 and so on. अगर 3 था तो यहाँ पे 2 था, n-1 है तो ये nth टर्म है बेसिकली, क्योंकि आपकी काउंटिंग जो है वो 0 से स्टार्ट हो रही है। ये यहाँ पे आपका माइनस बेसिकली 0 है, देयर इज नथिंग इन द माइनस हियर। तो यहाँ पे आपकी जो नंबर ऑफ टर्म्स है वो n है। सो यू विल हैव sin n5/2 by sin 5/2 into cosine of ओमेगा t माइनस, और ये जो लास्ट वाली टर्म हुआ इसके अपॉन 2। इन सब की सब टर्म्स का जो सम है, यहां तक जो सम है वो बेसिकली इस सिंपल एक्सप्रेशन से दिया जाएगा। इट्स अ सिंपल समेशन ऑफ ट्रिग्नोमेट्रिक सीरीज। किसी भी ट्रिग्नोमेट्रिक सीरीज का अगर आप समेशन करते हो तो यहाँ पे ये आता है। अब यहाँ पे आप नोटिस करो, देयर आर टू टर्म्स, वन जिसका टाइम फैक्टर से कोई लेना देना नहीं है, एंड द सेकेंड विच इज हैविंग अ टाइम डिपेंडेंस। The first one, which does not have anything to do with time, is basically your amplitude. ये आपका amplitude है। I have written it theta क्योंकि ये phi पे डिपेंड करता है, phi है वो आपका theta पे डिपेंड करता है। तो आपका जो resultant amplitude होगा वो basically आपका theta पे डिपेंड करता है। So that is why I have written it E theta. Well, let's first focus on the amplitude क्योंकि आप intensity observe करते हो, intensity is nothing but amplitude square. So we are first going to focus on the amplitude part here. E theta we said is equal to A sine n5/2 over sine 5/2, where phi we defined as 2 pi by lambda into delta sin theta. ये हमने define किया था phi को. In this expression now, if this is phi, तो n phi by 2 क्या होगा आपका? n by 2 into 2 pi by lambda into delta sin theta. 2 से आपका 2 कैंसिल हो गया, pi by lambda and delta sin theta. N times delta. If you go back a couple of slides here, we said that AN is equal to n minus 1 delta. AN is basically the width of the slit. So we said that B is equal to n minus 1 times delta. This is what we said. Now, if you let n run to infinity, now we are going to put the condition where we are saying that now let us put the limit where your n tends to infinity, क्योंकि आप एक finite slit में you can draw an infinite number of points. So initially we did took some n number of points. Now is the time to let run n from 0 to infinity, or rather put the upper limit of n where n tends to infinity in that case. If your n tends to infinite, then अगर आप उसमें से एक subtract करो, एक add करो, it would hardly make any difference. So that means I can say that B is approximately equal to n times delta here. So from here then, in this expression here, I can say that this is equal to pi over lambda into B sin theta. ये आपका pi over lambda B sin theta के equal हो गया है. Now, if your n tends to infinity, we said that your n phi by 2 is going to be approximately equal to this number, right? As I said before, but if your n tends to infinity, that means your delta would tend to 0. क्योंकि जैसे आप number of points infinite करोगे, points के बीच में separation है वो आपकी 0 होने start हो जाएगी. So अगर आपका delta tends to 0, in that case, look at this expression here. What would happen to your phi by 2? अगर आपका delta tends to 0, then your phi by 2 also tends to 0. If your phi by 2 tends to 0, in that case, your sin phi by 2 is approximately equal to phi by 2. So that means I can say that this expression is nothing but E theta A sin n phi by 2 की आप यहाँ से वैल्यू प्लग कर दीजिए, B sin theta phi by 2, डिनोमिनेटर में आपका phi by 2 आ गया, राइट? phi by 2 की आप फिर से यहाँ पे वैल्यू प्लग इन कर दीजिए इस वाले एक्सप्रेशन से. If this is n phi by 2, that means your phi by 2 is pi over lambda B over n sin theta, right? n को मैं इस साइड में लेके जा सकती हूँ. Then I can say that this is equal to A sin pi lambda B sin theta अपॉन phi by 2 की वैल्यू फिर से प्लग इन कर दीजिए, पाई ओवर लैम्डा B sin थीटा n आपका न्यूमरेटर में चला गया. यहाँ पे आपके पास पाई ओवर लैम्डा B sin थीटा न्यूमरेटर में भी है, डिनोमिनेटर में भी है. हमको इसके साथ में टाइम एंड अगेन डील करना है. सो लेट्स कॉल इट सम अनदर नंबर विच इज बीटा ही, where we are saying that we are defining beta to be equal to pi over lambda B sin theta. This is our beta. B is the width of the slit, lambda is the wavelength that you are using, and theta is the angle of diffraction. So this is now basically your amplitude. If this is your amplitude, then that means this displacement over here. This displacement, which was amplitude multiplied by cos omega t minus n minus 1 phi by 2. अब अगर आपका n tends to infinity, तो n में से एक सब्ट्रैक्ट करोगे कोई फर्क नहीं पड़ेगा. ये बेसिकली आपका n phi by 2 हो गया है. And n phi by 2 is nothing but your beta. हमने बीटा जिसको डिफाइन किया गया, बीटा इज डिफाइंड एज पाई ओवर लैम्डा बी साइन थीटा. पाई ओवर लैम्डा बी साइन थीटा ये भी है. सो दिस इज बेसिकली इक्वल टू बीटा. दैट मीन्स ये वाला जो आपका एक्सप्रेशन है, दिस एक्सप्रेशन हियर इज I can rewrite it as, let me write it here itself, ANA sine beta over beta cosine of omega t minus beta. ये आपका सिंप्लीफाई होके इतनी सिंपल टर्म में आ जाएगा, वेयर बीटा इज नथिंग बट पाई ओवर लैम्डा बी साइन थीटा, जहां पे ये क्योंकि n टेंड्स टू इंफिनिटी, उसमें से 1 सब्ट्रैक्ट करने का कोई मीनिंग नहीं होगा। n 5/2 जो है वो बेसिकली हमने बीटा डिफाइन किया है। एंड डिनोमिनेटर में आपके पास में, सॉरी न्यूमरेटर में आपके पास में ये वाली टर्म ई थीटा थी, जिसको अभी अभी हमने सोल्व करके वी हैव प्रूव दिस इज इक्वल टू एन ए साइन बीटा ओवर बीटा, जिसको कि हमने अभी अभी इसके इक्वल प्रूव किया है। So I have just plugged in the value of e theta na sin beta over beta cosine of omega t minus beta. अब ये वाली जो टर्म है ये आपका एम्पलीट्यूड है, बट हम इंटरेस्टेड है इंटेंसिटी में, एंड इंटेंसिटी इज एम्पलीट्यूड स्क्वायर, सो विल स्क्वायर दिस एम्पलीट्यूड and that would be basically your intensity, and then we will derive the condition of minima and maxima on the screen, कि कहाँ पे आप मिनिमम एक्सपेक्ट करोगे स्क्रीन पे और कहाँ पे आप जो है मैक्सिमम एक्सपेक्ट करोगे स्क्रीन पे. We'll derive that expression in the next class. But as I said before, single slit में I have done it individually, एक एक पॉइंट अज्यूम करके किया है. डबल स्लिट में हम ऐसा नहीं करेंगे. डबल स्लिट में what I'll do is that I'll start from this expression itself. ये वाला जो एक्सप्रेशन है इसमें एक और फेज हम डालेंगे and we'll be done with the expression. Anyone has any doubt in today's class?
Ma'am, can you switch to next page?
हाँ जी.
Ma'am,
हाँ जी.
ma'am, while doing the Newton's ring experiment, at one point we calculated the fringe width and like we found out that it was lambda by 2 mu alpha. And like
That
yesterday yes, ma'am.
that was in the wedge shape film. The fringe width we calculated.
That
Even
was not for
it is a
Newton's
type
ring.
of basically your wedge shape film, but the expression that we derived, that was before Newton ring experiment.
So, ma'am, that is not valid for Newton's ring.
It should be valid, because Newton ring is an example of basically your wedge shape film.
Ma'am, but yesterday while you were finding out the diameter, you said that the fringes are not equally spaced, but the
Mhm.
fringe width is constant. So how
Mhm.
come like both of them are true at the same time?
Okay, so there is going to be next class starting just in a minute. Let me come back with this question tomorrow. As soon as we start the class, I will first answer your question and then we'll move on further.
Okay, ma'am.
Okay. If I forget, just remind me in tomorrow's class.
Okay, ma'am.
I just have to sign out. Class time is over.